Hello, everyone. Welcome to our Monday afternoon seminar. Today, it's a great pleasure to have with us Irene Valenzuela. So Irene got her PhD here at the IFT with Luis and continued her career with several postdocs in the Max Planck Institute at Utrecht University, at Cornell, and finally at Harvard, after which she came back to the IFT as a Monica Hall Fellow. She recently also received the Young Researcher Prize from the BBVA Foundation and also an ERC starting grant. So today she will tell us about the Swampland conjectures. Irene, please, you have the floor.
Okay, thank you. Thank you for the introduction. Thank you everyone for coming. It's a bit of a pity to be giving this seminar online now that I'm finally back at the IFT and we are just in the same building, but what can we do? So I will try to make it, I don't know, as dynamical as possible. I will go slowly, but please, if you have any question at any moment, anything that comes to your mind, any comments, just do it so we can try to emulate as if we are in person downstairs. Okay, so my plan is to talk about mainly this recent paper with Yuta Hamada, Miguel Montedo, and Kumrun Bafa in Harvard, in which we try to provide some more evidence for some of these Swampland conjectures by thinking of black hole physics. So as I said, I will go slowly. So even if many of you probably already know very well what the Swampland program is, let me just at least quickly remind the main messages. Okay. So I think the most important message behind the Swampland is that not everything is allowed. Okay. So that you can construct your favorite effective field theory that describes some particle physics or cosmology, and you can follow the rules of quantum field theory. You can make sure that it's anomaly free, that is unitary, at least at low energies and so on. And the point is that this is not enough. Okay, this is not enough to guarantee that this effective field theory will be consistent with quantum gravity at higher energies. So we use the word Swampland for those effective field theories that seem apparently consistent at low energies, but still cannot be UV completed. Okay. And this word is used in opposition to the landscape, which are those effective field theories that can arise as low energy limits of a quantum gravity theory like string theory. So the whole game is trying to understand what are the rules, like what are the rules that we have to impose in these effective field theories so that they belong to the landscape. Okay, so what are the constraints that an effective field theory must satisfy to be consistent with quantum gravity? And of course, this is a very ambitious program, right? Because we don't understand quantum gravity so well yet. But I think, at least in my opinion, it's very important because we are trying to understand what is the UV imprint of quantum gravity that remains at low energies. And if there are new constraints that we need to satisfy, they can have interesting phenomenological implications because they can be used as new guiding principles to construct beyond the standard models, and can also help to bring new insights to solve the naturalness issues in our universe. Because what seems natural from a quantum field theory perspective might not be natural from a quantum gravity point of view. Okay, so the take-home message that I will recall several times during the talk is that the EFT expectations that we have when we work in quantum field theory can fail in the presence of gravity. Okay. Any general question, comment? Okay, so how do we work in the Swampland program? Well, the first step is try to identify some universal pattern that we think could be general of quantum gravity. This is formulated in terms of some conjectures that, of course, the point is that we don't have a complete framework of quantum gravity where we can just simply prove these things, but we have many things to play with. We can, of course, we have to test these things in string theory because regardless of whether it describes the universe or not, it's a consistent theory of quantum gravity. So if we are claiming to have universal patterns, they should be realized in string theory. And also string theory give us the framework to provide very quantitative and sharp tests of these conjectures. Now, of course, if we want to say that these constraints are more general, like our general quantum gravity, we should try to understand why. I mean, try to explain what is the underlying principle. In other words, like what goes wrong if you don't satisfy these constraints in a more general way. Maybe we cannot prove it completely, but we need to have some more heuristic arguments to understand it, to make sure that the constraints that we derive from string theory are not just a matter of the lamppost. No, that is not just a technical thing, but it's more a fundamental constraint. And then you can try to study and understand what are the phenomenological implications that could have for our universe, both for particle physics and for cosmology. Okay, so these universal constraints are typically motivated by string theory and black hole physics. And I have here a map that I like to show with the most important ones. In fact, I put in purple the ones that are like at the core of the Swampland program. And I'm not gonna go through all these conjectures. What I want to do is precisely to extract the main points, like the common features of them. So one of the most important developments in the past few years is that we are discovering that all these constraints are not independent, but they seem to be correlated, which seems that, I don't know, at least this hints for me that they might be different phases of the same underlying quantum gravity principles that we are starting to discover. So one of my goals is always try to understand these connections to see if we can reduce all these conjectures to the minimum number of statements or principles that would reproduce everything. So for example, if you see the first row, like the 3 on the top, basically all these can just be replaced by the statement that there are no global symmetries in quantum gravity, in the sense that a global symmetry must be broken or must be gauged, must be associated to some gauge degree of freedom so that we can measure the symmetry from far away. And if we extend our notion of global symmetry as it's happening in the community in the recent years, to include both non-invertible symmetries and topological symmetries that are not associated to gauge or matter degrees of freedom, but purely about the topological charges that come from gravity, then we can unify all these conjectures that we had before. Okay, so it's just about extending what is this notion of global symmetry that is not consistent in quantum gravity. And this has different facets. Okay, for the next row, we can also try to extract some general feature that is both represented by the weak gravity and the distance conjecture, which is the fact that the EFT, the effective field theory, can break down earlier than expected. Okay, so that quantum gravity is putting constraints on the field spectra such a way that if you try to have a small gauge coupling or a large scalar field range, you are going to get new physics, you are going to get new degrees of freedom that are becoming light, and this is going to invalidate the effective field theory. Okay, so basically when you take some limit on some parameter that in fact is going to restore some global symmetry, something has to go wrong, the EFT has to break down, and how this happens is because we get towers of states becoming light. Okay. And then for the last ones, the last ones are more recent conjectures, that what they do is to study the constraints that appear in the scalar potential. Okay, so for example, the presence of these towers of states are going to have some consequences. And this can lead to very surprising constraints on the scalar potential and the possible landscape of vacua that we have. No? And here is where we have all these discussions about whether we can have the Sitter vacua or whether we can have scale separation in the sense of that if we have extra dimensions, that they must be much smaller than the scale associated to ADS or the Sitter. Okay, so in this talk, I'm going to focus on this middle row. Okay, I'm going to focus on this message that the EFT can break down earlier than expected because we get new physics becoming light, okay, new degrees of freedom. But before entering into that, let me just make one more comment, which is that these constraints, I mean, these are things which are very surprising from a QFT perspective, because in quantum field theory, it's completely fine to have global symmetries. It's completely fine to have small gauge couplings, right? Like we can have a perturbative gauge theory and there is nothing wrong. It's even good because we have control over the theory. There is nothing wrong with having a large field range as long as the energies remain below the cutoff. And there is nothing wrong with engineering the scalar potential as you wish, as long as everything is anomaly free and so on. So these are examples that make manifest this message that, as I was saying, that sometimes EFT expectations can fail in the presence of gravity. And this is because the UVIR mixing that is induced by quantum gravity, and this breaks down with the typical expectation of separation of scales that we have from a Wilsonian quantum field theory approach. Okay, so it's not just that we have constraints on the non-renormalizable couplings, no? Like typically the way to think like Wilson, no, is that we have some renormalizable part and then we have an infinite tower of operators which are UV sensitive, no? But typically we expect that we can work at the energies below the cutoff such that all these operators will not be very important, they are irrelevant in the infrared. And the physics at that energy scale should not be very sensitive to the physics above the cutoff. Now, the point here is that it's UVIR mixing. So the constraints I'm giving you is not just about the tower of irrelevant operators, it's also about the renormalizable part, about the relevant ones, okay? So the point is that not every EFT, as I was saying at the beginning, that you construct will be allowed in the end, okay? Will be consistent with quantum gravity. And that's why we can give, even if the quantum gravity scale is very high in energy, like the Planck scale is very high, and it seems that it's not relevant for our universe, that's not true, because we must have non-trivial constraints at low energies that come from this UVIR mixing. Okay, any question? Or comment? Everybody agrees? Okay, good. So let me then go to the main part of the talk. So I want to focus on these asymptotic towers of states that appear. Okay, so what I'm gonna do is I'm going to review very briefly what we know about it, where these towers are coming from, and I will show you in one slide what is the evidence that we have. And then what I'm going to do is to try to give a bottom-up explanation. Okay, so at the moment, all we have is string theory evidence, but it was missing some bottom-up explanation of why we get these towers when the gauge coupling is small or the large field range, or the field range is large. Okay. Okay, so as I was saying before, if the expectations can fail, one example is that the cutoff can be much lower than the Planck scale, the quantum gravity cutoff, if we have small gauge couplings, large field ranges, or approximate global symmetries. And this happens because there is an infinite tower of states that is becoming light when you try to engineer one of these things. Okay, so this is something which is surprising from an EFT perspective, but it's very natural from string theory. Okay, because in string theory, whenever we can change the value of the gauge coupling by moving in the field space of the theory. So all the parameters in string theory will be parameterized by the vacuum expectation value of some scalar fields. So we can move in this field space and then change the value of these parameters, and each point will be like a different potential vacuum. And what happens is that when we try to make the gauge coupling very small or the field range very large, what we are doing is moving towards the boundaries of this field space. Okay, we are moving like an infinite distance in this field space. And whenever that happens, we always get like we always get that the description that we were using fails in favor of a new description of the theory. Okay, so there's always like a duality that arises and gets manifest in these infinite distance boundaries, which points that there's a new weakly coupled description that takes place and that is given by this new infinite tower of states. So you cannot have a single effective field theory which is valid for a large field range of the field space. Now, these string dualities is like the first thing that you learn when you start with string theory, and typically they correspond either to the compactification limits, in which you grow some extra dimension, or string perturbative limits, in which you get it's a limit in which some string become tensionless, and then you get sensitive to all the string modes, and you cannot work with quantum field theory anymore. Okay. Now, at the moment, these are the only two types of limits that we know, but it's an open question whether there could be something else, like whether you could have excitations coming from high extended objects and so on. Okay. Now, I put here just, I don't know, for the people that maybe have heard about the conjectures, like a summary of what they are. I mean, it doesn't really matter for my talk. All that matters is that we are going to get towers of states when the gauge coupling is small or when the field range is large. But just so you know, this is more quantitatively explained in terms of these two conjectures, which are the weak gravity and the distance conjecture. Okay, so the distance explicitly says that you should get an infinite tower of states becoming exponentially light at every infinite distance limit in the modular space. Okay, and the weak gravity conjecture, the states are going to become light in terms of the charge. Okay, so you need to have some state whose mass is smaller or equal than the charge, and since the charge depends on the gauge coupling, when the gauge coupling is small, then the state will be light. Okay, will go to zero. And we see that this is also motivated by black holes, but what we observe in string theory is that it's not only one state that satisfies this, but we actually have like infinitely many, like a sublattice or a tower of them. Okay, so as I said, the message is just that when we have weakly coupled gauge theories or large field ranges, this is possible in quantum gravity, but come at a price, in the sense that the UV cutoff is going to go to zero. So you have to be very careful that the energies of the process that you want to describe with that effective field theory are below this cutoff, which is becoming very small if the gauge coupling is small or the field range is large. Okay. Okay. So before getting into the evidence, let me mention a bit what are the phenomenological implications of this. Okay.
Irene.
Yes, please.
Let me ask you a question. It's a very simple question. Is that you say that when G-Jalmils goes to zero, you automatically get a tower of light states, right? Mm-hmm. Now take QCD in the Larsen limit, planar limit. Mm-hmm. Then the coupling goes like 1/n. If I take the real planar limit, the coupling G goes to zero. Tough coupling not, but the G-Jalmils coupling goes to zero. Mm-hmm. What is the tower of light states that you get in normal QCD in the Larsen limit?
So if I'm thinking of ADS-CFT, there is a clear answer there. Like for
you
example,
are what?
If I'm thinking in ADS-CFT in the context
no, just take QCD, standard QCD.
So what this is going to tell you is that if it's really becoming weakly coupled, I mean, if you go to the limit in which the gauge coupling
can be weakly coupled in terms of G, but not in terms of tough coupling.
Yeah,
that's
okay.
I want to ask you, okay, is G what is important for you that when G goes
it matters, yeah. I mean, what matters is that you're restoring a global symmetry. So it matters that you are turning off the dynamics of the gauge field, right?
This is not the case in Larsen. Although G
so that's the point. Like you should, exactly. So the point is that the problem appears when the gauge symmetry, I mean, we have some symmetry which is gauged, is going to become global. because the dynamics of the gauge field disappears, and therefore you ungauge the symmetry, and then you should get the towers of states. Now, I should also say that in the case of non-abelian gauge theories, it's a bit more tricky because since the gluons, right, are already charged under the gauge theory, they already satisfy the weak gravity conjecture. So this conjecture becomes more powerful for abelian theories, because then you really need to have matter to satisfy it. But
then your statement G YALM is going to 0 sorry, implies a tower of light states. How I can understand it for QCD in Larsen limit?
So the way I say it is
normal QCD,
for
no
abelian.
Symmetric, nothing like that.
Yeah, exactly. So the way I said it is for abelian. Now, for non-abelian, as I said, it's kind of an open question how the weak gravity works, because exactly like the gluons are already satisfying the weak gravity, so it seems that it doesn't require you to have new states. And there are people that are trying to understand this better.
No, you could say something clear, because in the Larsen limit, even G YALM goes to 0. The baryon becomes extremely massive. Now, if whatever coupling to gravity you have, the baryon will become a black hole, because with the mass of the baryon will go like n. If n is extremely large, except if you put the Planck mass equal to 0, then this will be a black hole. Then I thought that probably you can claim that when you couple, that this cannot be consistently coupled to gravity, the planar limit. This is a problem.
I would say, so
the end that I am talking about is the number of colors. This particular.
Yeah, I know. My answer is that, yeah, you should do it in terms of how approximate the symmetry is. So about turning off the dynamics of the gauge field, the propagator. That's what matters. Okay. If you are turning off the coupling of this propagator to the charge, then something has to go wrong, because you are restoring the global symmetry and you should get an infinite tower of states. If you do it in a different way that you don't restore the global symmetry, then I don't think
probably then your statement will be that when the top coupling goes to 0, you get the infinite tower of light states, but not when G YALM goes to 0.
Yeah.
Okay. That's simply common because, one simple example when G YALM goes to 0 is the planar limit, okay?
Yeah, this is for the abelian ones. I mean, like this is just a U1, but yeah, otherwise one has to refine it.
Okay.
Okay, more comments? Okay, so let me just mention briefly why this is interesting. Well, first, yeah, I mean, with the weak gravity conjectures, you can use it to constrain beyond standard models in which you have some dark sector with a very small gauge coupling, or like this milli-charge dark matter, or you can also use it to constrain inflation when you have large axionic decay constants, because an axionic decay constant is like a gauge coupling of a zero form gauge field, an axion. And the distance conjecture, you can use it in general, no? Like to constrain theories with large field ranges, like in inflation. So what is happening here is that, yeah, since the cutoff is going to 0, this is putting you an upper bound on the maximum field range that an effective field theory of a given cutoff can describe. Now, as an example, we can check what are the constraints on large field inflation, okay, in which we should at least require that the Hubble scale is smaller than the cutoff of the effective field theory. And then this translates to an upper bound on the field range in terms of the Hubble scale during inflation, which can be written in terms of the tensor to scalar ratio. Okay, and the point is that this relation between the field range and the tensor to scalar ratio goes in the opposite direction than the least bound. Okay, so there will always be only a finite region that is consistent with the slow roll inflation and quantum gravity. Now, exactly what is this region? To give a quantitative bound, we need to know exactly what is this lambda that I put here, this parameter, which is the exponential rate of the tower. Okay, that tells us how fast tower is becoming light. Now, this is where a lot of work is dedicated in the context of string theory. I try to give bounds. So we have already bounds for this parameter, which is some order 1 number. And this is going to tell us exactly like what models are ruled out and which ones are not. Okay, but as at least the conclusion is that some models are ruled out, not all of them, and it depends exactly on the value of this parameter. Okay. So what is the evidence that we have for the existence, no, of these towers of states? Now, most, if not all, the evidence, actually, well, I would say all the quantitative evidence comes from string theory, in which we have checked in a very systematic way all the possible limits, weak coupling limits, and infinite distance limits that you can have, and identify explicitly what is this tower of states that is becoming light. More recently, we are also studying this in the context of ADS-CFT, because this translates to some interesting features in the conformal manifold, and one can aim to prove this conjecture by using conformal bootstrap techniques. Now, the point here is that, as I said at the beginning, it's an observation. I mean, the presence of this tower of states is very natural from the point of view of string theory. It's linked to all these string dualities. But it was not clear why. I mean, from a bottom-up perspective, like why we should get these towers, no? What goes wrong if we don't? What goes wrong with quantum gravity if they don't appear? So, a promising avenue to try to give some explanations of these features that we observe in string theory is think about black hole physics. Okay, it's a nice, it's a promising avenue. Now, for the distance conjecture, I mean, like the tower of states becomes light with the field range. There was simply no argument at all related to black hole physics that could really tell us why you have this infinite tower of states decaying exponentially. For the case of the weak gravity conjecture, so that we have the states at the weak coupling limits, there is actually a connection with black hole physics. Okay, you can also derive the weak gravity conjecture by requiring that extremal black holes must decay. However, the point is that this only allows you to provide an explanation for a mild version of the weak gravity conjecture, in the sense that you just need to have a single particle satisfying the weak gravity conjecture to allow a black hole to decay. But what we observe in string theory is something much stronger than that. We don't observe only a single particle, we observe infinitely many. So why do we need this quantum gravity cutoff go to 0? Why we get infinitely many states and not just one? So what I'm going to do in the rest of the time is to provide some new argument in support of these asymptotic towers of states, namely in support of the cutoff, the quantum gravity cutoff going as the gauge coupling or the field range based on finiteness of black hole entropy. Or more generally, at the very end, I will speculate that maybe it's not just about finiteness of black hole entropy, but more generally about finiteness of quantum gravity amplitudes. And for those of you that know what this is, I will show you some connection with the emergence proposal that I will explain later. Okay, any question? Okay, so let me also make one comment about finiteness. So notice that many of these Swampland conditions emerge when we replace something infinite that can happen in quantum field theory by something finite. And in practice, I mean, very naively speaking, this kind of happens because the Planck mass is finite. Okay, so for example, the weak gravity conjecture is telling us that we cannot decouple some particles, like we cannot send the mass to infinity, or we cannot send the gauge kinetic function, or like the inverse of the gauge coupling, to infinity if the Planck mass is finite. Okay, in the moment in which the Planck mass is infinite and we decouple gravity, then the constraint disappears. Okay, and there is no bound anymore. For the distance conjecture is the same. It really matters that you have the Planck mass, and this gives us a finite upper bound on the field range, which otherwise could be infinite. The same, I mean, there are also constraints and expectations about having only a finite number of degrees of freedom below a cutoff in a quantum gravity theory. and also having only a finite number of vacua. Okay, we believe that the landscape, even if it's huge, is still finite. So what we want to do also with this program, with this paper, is to initiate like some program to view all these Swampland criteria as coming from some finiteness of quantum gravity amplitudes. Okay, so try to give some unification to all these statements. Okay. So any question? Otherwise, I will give you now the argument based on black holes. Okay, so let me give you what is the argument that we have. I mean, why we can try to argue for the presence of this tower of states just thinking of black holes. Okay, and I will try to go very slowly so you can also ask any question at any time. Okay, so the philosophy here is I'm going to try to understand what goes wrong if I try to engineer some large field range or some weak coupling limit in a given effective field theory. Okay, so for example, when you have some solitonic object, this is going to induce some back reaction, right? That it can change the profiles of your fields and can change the value of the gauge coupling or the scalars as you approach or go far away from the object. And we try to understand what goes wrong then, like if this object generates a very large field range or a large variation of the gauge coupling. This, let me just put some references. This was a very useful avenue in several papers. The difference here is that we are going to consider small black holes, okay? So I will explain what they are. Okay, so let's just take Einstein-Maxwell dilaton theory, in the sense that I just have the Einstein term, the gauge field, with a gauge coupling that is parameterized by some scalar, by some dilaton. Okay. In such a way that the gauge coupling goes to 0 as the field range goes to infinity. Okay, so this is the typical scenario that happens in string theory. I want to understand from a bottom-up perspective what goes wrong if this happens. Okay, now we can look for black hole solutions to this theory. Okay, we have this ansatz, we just have to solve the equation of motion, and we are going to look for electrically charged solutions. Okay, so I only have some electric charge, not magnetic. Now, due to the attractor mechanism, because this is the truncation of n equals 2, the dynamics is captured by this effective theory that I wrote here, this Lagrangian, subject to this constraint if I'm looking for extremal solutions. Okay, extremal means that the value of the mass will be as small as possible for that charge. Okay, so I just have to look for these solutions, and the point is that the black hole is going to induce a running of the scalar field and the gauge coupling as we approach the horizon of the black hole. Okay, so I'm locating the horizon at tau equals minus infinity. This is going to be my coordinate, my radial coordinate, and tau equals 0 will be the infinite far away. Okay, so extremal black holes, sorry, as you can see here, they satisfy this condition, and since this is positive definite, they are going to satisfy this inequality. Okay, this is just because they are extremal black holes. Now we can use this to write an upper bound on the area of the horizon. Okay, the area of the horizon is given in terms of this conformal factor, this radial coordinate in this way, such that by integrating what we have here before, we can derive this upper bound on the area, which, as you can see, depends on the gauge coupling. Okay, so there are two possible situations. If the gauge coupling is constant, so it's not parameterized by some scalar field and it always remains constant, then this bound is not very interesting in the sense that it just tells me that this area has to be positive. I mean, there is no upper bound, okay? And these are the typical Reissner-Nordstrom black holes, okay, the charged black holes. Now, if the gauge coupling goes to 0 at the horizon of the black hole, then because of this upper bound, the area also has to go to 0. And then this is what it's called a small black hole, okay, because the area is becoming very small. Just to give an example, if the gauge coupling is an exponential of the scalar field, as happens typically in examples, then the field range is the scalar field is going to get a logarithmic profile when you solve the equation of motion in such a way that indeed goes to infinity at the black hole horizon, where the area of the black hole goes to 0. Okay. Okay, so the message is that large field variations associated with weak coupling limits, when the gauge coupling is going to 0, are confined near small regions in space and are associated to these small black holes, okay, because these black holes are becoming smaller and smaller. Now this,
sorry,
yes.
me. By small, you mean of Planck length size?
You will see. So from a bottom up, it seems small. Of course, this is going to break down at some moment. And the goal will be to determine exactly what is the cutoff. And it's going to be lower than the Planck scale.
But then it's not a black hole.
You will see. Let me some slides. You will see what I mean. So we are going to determine exactly, when this effective field theory description of the black hole stop making sense. Okay. Okay, so yeah, I mean, small black holes, I mean, if I tell you that you have some nearly point-like objects, this will sound weird to you. Okay, like what's going on? Now you tell me that in this simple effective theory, we have infinitely many point objects because we can just construct black holes with different values of the charges, okay, and that's it. So something should go wrong here. Now, what happens in practice is that the area receives corrections, okay? Like this effective field theory is not enough. You receive corrections that will produce some finite area, no? And these corrections will be of order the cutoff of your EFT. Now, what we want to do is that instead of, I mean, we will forget about the string theory embeddings. We just want to check what is this small area, what is this cutoff? So we'll see that if the cutoff was infinite, if I could really trust these black holes, they would lead to a violation of the Bekenstein bound, unless the EFT cutoff decreases precisely as dictated by the distance and the weak gravity conjecture. Okay, so we are going to derive how this cutoff has to behave such that there is no problem. Okay, so what is this Bekenstein bound? So what I'm going to apply is this entropy bound. That's if I have some region of size L, I have a box, I cannot have more entropy inside this box than a Schwarzschild black hole of the same area, okay? So this is going to constrain how many states I can put in this box, okay? Because otherwise the entropy will be larger than the entropy of the black hole. Now, of course, this is going to be violated if I have point-like objects, okay, because then I can have infinitely many, the area will be infinite and will completely violate this entropy bound. But as we were saying, what happens is that the EFT is going to break down. So these black holes, these small black holes are going to get some effective area that is dictated by the cutoff of the theory. And this is going to solve the problem, okay? And the goal, as I said to Cesar, is to determine from a purely bottom-up perspective how the cutoff has to behave to avoid the violation of these entropy bounds in a quantitative way. Okay, so let's do it, okay? First of all, how we are going to determine where this effective field theory description breaks down? Well, the point is that as we approach the horizon, the gradient is not only that the scalar goes to infinity, but also the gradient of the scalar field diverges. Okay, so in the moment in which this kinetic energy, right, is above the cutoff, it doesn't make sense anymore. So we are going to take as a proxy of when the EFT breaks down, the value of this gradient of the scalar. Okay, it's just a proxy. So when the gradient of this scalar is of order the cutoff, then this description breaks down. I cannot trust anymore this solution. Okay. Now, using this inequality, which just comes from requiring that it's an extremal black hole, and the expression of the area of the black hole, I'm plugging this here in this condition of the gradient, we get a relation between the cutoff and the area of the black hole. Okay, so for a given charge, the maximum area of that black hole, sorry, the minimum area is going to be given by this expression of the in terms of the cutoff of the theorem. Okay, so this is the size of the black hole that we can trust before the EFT breaks down. Okay, now this is the condition we have. So let's apply the entropy bound. Okay, so how many black hole states can fit in a box of size L? Now to do that, we are going to count all of these states at a given energy, which is the maximum energy that I can put before the box collapses to a black hole. And the point is that here, since the gauge coupling is going to 0 and they are becoming point-like, the interactions are becoming very small. Okay, so it's weakly coupled. So in this limit, all the black holes with different values of the charges count as different species. Okay, because there are no interactions among them. So I can, in the limit, I can neglect to form bound states. So at sufficiently weak coupling, any small black hole of a charge Q will count as an additional species when counting the entropy. Okay, so if I want to require that the number of species, which is given by the maximum charge that I can put, is smaller than the entropy of a black hole of that size, which is as given by the area of the black hole, I get that the Q, the maximum charge that I can put inside of this box is smaller than the area. And if I combine this with the inequality that I got before that was relating the cutoff and the area, I just get that to avoid violation with this entropy bound, the EFT must break down as the gauge coupling in Planck units. Okay, and this is precisely the behavior of the cutoff that is dictated by the weak gravity conjecture. Okay, so without assuming anything about string theory or the corrections or the UV completion, just by requiring that I satisfy these entropy bounds, we can derive that the cutoff has to decrease sufficiently fast, particularly in terms of the gauge coupling, to give rise to some effective area for the black hole, such that I cannot put too many inside of the box and violate this entropy bound. Okay, so 2 comments about this. First is that this supports a strong version of the weak gravity conjecture than the typical one coming from black hole instability, because this is about entropy bounds. So it's not enough just to add a new state to solve the problem, because then we can run the argument again and it doesn't change. We really need a full breakdown of the effective field theory. Okay, so this cutoff that we are talking about is like a quantum gravity cutoff. So we need to have, typically in order to have a full breakdown of the EFT, it's not enough just to have a few states becoming light, you need to have infinitely many states. And that's why I say it supports a stronger version of the weak gravity conjecture by telling you that you need to have many, infinitely many states, such that you cannot trust this computation anymore. And it also makes quantitative the typical trouble with charge remnants that maybe, if you have heard of the Swampland program before, is used to argue for the absence of global symmetries and so on. It was difficult to argue for it in a quantitative way for charged black holes, because actually this doesn't work for Reisner non-strong black holes. One really needs to consider these small black holes to get a violation of the entropy bounds. Any question?
Irene, hi, can I ask you a quick question?
Yes.
So I understand your argument, but so curvature corrections, higher duality corrections would also give you a little increase in the area. So I agree with you that this is a much stronger argument, but I was wondering if you have kind of taken into account how the standard higher derivative correction would contribute to your cutoff, because I feel like there should be some interplay between the two.
Yeah, the thing is that here I am agnostic about how the IFT is breaking down. It could be that it's breaking down because there are higher derivative corrections that I need to take into account, higher curvatures and so on. And and that could be the resolution. The point is that from a bottom-up perspective, I know that needs to happen at this scale. So it could be because many things. I mean, here I think maybe you are pointed of how you know, why an infinite number of states, no? And maybe not just like higher derivative terms. Maybe that's the.
I guess my point is I would expect not to trust that action at some point. Right? The action would just not be a good description, and then it would be natural to add some kind of higher derivative terms, and then those may change the argument.
Yes,
it would also correct.
Exactly. So yeah, exactly. So as I said, what happens when you have the infinite number of states is that what you are going to see in the IFT is that they are going to induce higher derivative terms, and this is going to correct the solution, and that's why you will get an effective area in the end. Here, as I said, I want to be agnostic about how exactly it is solved. I'm saying that I'm expecting to have an infinite number of states behind this, because if I just have a finite number of them, typically that's not enough to modify this solution enough to avoid this entropy bound, because this is about counting states, right? So it's really like something drastic has to happen. It's not just counting one more or two more, right?
Yeah,
that's
I agree with
the
that.
idea behind.
Thanks.
Yeah.
Sorry, I didn't understand. What is the difference between your argument and the very old argument that is the species argument that Bekenstein already raised when he wrote his original paper? I put in a box a system with certain energy and increase the number of species, I violate the Bekenstein bound. What is the difference between this, that we know more or less how to solve, and what you are saying?
Yes, let me tell you. So the point is that in the typical argument, I'm thinking of adding light particle, right? Like light species inside of the box. And what this argument gives you is the species bound, right? It gives you a bound of how many species you can have.
This is not necessarily the case, but okay. One way to address this problem is to introduce the species bound.
Okay, one resolution, okay, let me say, the typical resolution, the canonical resolution to that problem is that you have a species bound in the sense of how many states you can put in the box. Here, the point is that I cannot take that resolution because these are black holes, so I can always construct black holes within my IFT. It's not about constraining the field spectra of the theory. So that's the difference. The type of argument is the same. It's the same idea. It's the same idea than for the species bound. I just have many states in the box, and I want to count how many I can have, such that I don't violate the Bekenstein bound, so that the entropy is smaller than the entropy of the black hole. Since I cannot resolve the problem by constraining how many states I have in my theory, because these are black hole solutions that I can always construct, then I have to resolve it by decreasing the cutoff of the theory. And that's the conclusion. Yep.
Okay, this is okay.
No, thank you for the questions. More questions? Okay. So this is, as I said, it's it's the first argument we have given that supports something stronger, than just having one particle satisfying the gravity, but something more. And it's because, it's based on these entropy bounds and not just instability of the black holes. Now, it also provides a black hole argument for the distance conjecture, in the sense that morally, as I said, we expect that this breakdown is given by infinitely many fields. So it's telling you that when you have this large field range, you need to have an infinite number of states becoming light. Now, of course, it only works if the large field range is associated to a weak coupling limit, because these are charged black holes, so it really matters that I have a gauge coupling that is going to 0. And if the gauge coupling goes exponentially, as happens so far in all the examples, then the cutoff, the mass of the states will also go exponentially on the scalar field. Now, as I said, this is the typical behavior that we observe in string theory. interesting question is whether this exponential behavior is just a matter of the lamppost or there is a fundamental reason for that. This entropy argument is not enough to give you this exponential behavior. But as I will maybe mention a bit later, there are other arguments based on the emergence proposal that tell you that whenever you have this infinite tower of states becoming light, the quantum corrections from integrating out the towers are going to induce this exponential behavior for the gauge coupling and therefore for the cutoff. Okay, so the question that would remain is whether any infinite distance limits corresponds to a weak coupling limit, or whether we can have more general infinite distance limits that do not correspond to weak coupling limits, and therefore this argument wouldn't be enough in that case. And here, this is just a question for the people. I mean, every example I've seen in string theory, there is always a vanishing P4 gauge field asymptotically when the field range becomes large. I believe that it's something general because I think there is always, like in all these dualities, there is always like a weakly coupled description of the theory that emerges. So there is always some sort of small gauge coupling that arises, but it would be nice to understand this better. Okay, so to finish, and I think probably 5 minutes is even enough. I will just give you a few comments about how to understand this story a bit more generally, okay, and how maybe to relate it to the finiteness of quantum gravity amplitudes. Okay, so the argument I give you, well, I really like it. I mean, I think it's nice, but of course, as I said, it works if there is a weak coupling limit. Okay? Now, it's interesting to check whether it's possible to give another argument for the presence of the tower of states whenever the field range is large, regardless of the gauge couplings, okay, regardless of whether there is a gauge coupling that goes to 0. So try to give an argument of why non-compact scalars are not allowed in quantum gravity. So here I can give you some argument, at least some heuristic argument, that okay, you can take some scalar field theory, okay, which is non-compact, okay, so the scalar field can take any value, and compactify to one dimension, okay, so quantum mechanics. Now in quantum mechanics, the partition function is going to diverge if the scalar is non-compact, because I'm going to have a continuum of momentum eigenstates, and this is going to make the partition function diverge. Okay, so non-compact scalars are associated to these divergent partition functions. And the only way to keep this partition function finite is to have the cutoff also decreasing with the field range as the field range goes to infinity. Now, this argument is not strong enough to give the exponential behavior either, but it already tells you that something seems fishy, no, with these large field ranges. And maybe let me say quickly, as I said before, one can try to argue for the exponential behavior if one combines these arguments with emergence proposal. Okay, so as I promised, let me give you just a few words about what the emergence proposal is. So the idea is that the infrared effective field theory, the dynamics, all the kinetic terms that we have actually emerge from integrating out all the massive states that you have. And this is turning the logic of the conjectures in the sense that these conjectures are telling you that when the gauge coupling is small or the field range is large, you get the infinite tower of states. But the emergence proposal is telling you that, well, you have a gauge coupling which is small and you have a field range that is large because this arises from quantum corrections of having the infinite tower of states becoming light. Okay, so it's telling you, if you have the infinite tower of states becoming light, you are going to give to produce this behavior on the gauge coupling and the distance, no? the metric on the field space. And one can just derive, actually, like just in one line, if you compute, for example, quantum corrections to the field metric, these are going to scale always in this way if we compute the corrections of an infinite tower up to the species bound. And when we integrate this metric to compute the distance, this distance is always going to diverge logarithmically with the mass, so that the mass is going to behave exponentially with the field. Okay, and this is how one can derive the exponential behavior. Okay, so this is a proposal we had a few years ago when we were trying to understand these conjectures also from a bottom-up perspective. But here there is an assumption, which is that we are assuming that, yeah, everything emerges in the infrared, that there is no already a divergence of the distance in the UV, but that the scalars are compact in the UV and you just see the infinite distance when you flow to the infrared. And why the scalars should be compact in the UV was an assumption that was not very good justified, but again gets correlated to requiring that the partition function does not diverge. So what I'm telling you now about the partition function is like a way to motivate that these fields in the UV completion should be compact. And then when you have a low energy effective field theory, you can still see large variations, but this arises just because you have these towers of states that are becoming light and generate this. Okay. So just to finish the talk, you should wonder why this partition function should be finite. And this is what we are trying to explore now. I mean, whether this should be like a condition coming from quantum gravity, no? Let me just mention here. So whether finiteness of quantum gravity amplitudes is something that we should impose in any quantum gravity theory. It's kind of a generalization of requiring finiteness of the black hole entropy, right? It's like the black hole entropy is an example of this, but maybe more generally, what is behind many of these conjectures is this finiteness of some quantum gravity amplitude, okay? So that's something to explore in the future. At the moment, it's just very speculative, okay? So I don't want to say more about it, but just something to keep in mind that maybe is what is unifying all these Swampland statements. And something which is interesting is that if we think that indeed finiteness of quantum gravity amplitude is something that we should impose in quantum gravity, this can also explain finiteness of quantum gravity vacua, okay? Because in a few words, we can always take a theory with many infinitely many vacua, and if we compactify to quantum mechanics again, the wave function will be able to probe all these vacua, and the partition function will again diverge. Okay, so if we want to have a finite partition function, then we must have only a finite number of vacua below a certain cutoff. Okay, so I think this is enough. I think I can stop here and ask for questions. So let me conclude. I think the message I like to convey is that consistency with quantum gravity can be more important than what we think and have important phenomenological implications and give non-trivial constraints in the infrared because not every EFT is allowed. And one of the most important Swampland statements is that the EFT is going to break down if a gauge coupling is very small or a field range is very large because there is an infinite number of states that becomes light. And so far we had a lot of evidence from this coming from string theory, but here I show you at least some argument, some bottom-up argument based on black holes, based on requiring finiteness of the black hole entropy that can motivate why we get these towers in those cases. And more generally, something to explore in the future is try to generalize this and understand whether all these Swampland conditions can be understood as consequences of finiteness of quantum gravity amplitudes. Okay, so thank you for your attention. Let's see if there are further questions.
Okay, thank you, Irene, very much for this very nice talk. So we have time for questions from the audience. Questions, comments, doubts?
Don't be shy.
Especially the students are encouraged to ask questions.
Irene,
Yes.
you said at the beginning that in the context of this Swampland distance conjecture, when a module goes to infinity, a global symmetry restores. What is the global symmetry in this case?
Yeah, so, okay. So this is something that comes from observation of the examples, okay? From a bottom-up perspective, I don't have any reason why that should always be the case, okay? It's clear the opposite. Like if you have a global symmetry, this is going to be pushed at infinite distance because they cannot occur in quantum gravity, but it's not obvious that at infinite distance, you will always restore a global symmetry. Now in examples, it seems that there is always some type of gauge coupling that is becoming light, it's going to zero. And when a gauge coupling goes to zero, the gauge symmetry becomes a global symmetry. So you restore that global symmetry. There are other examples, there are other types of symmetries that arise sometimes. For example, when you have this infinite tower, you also have like some discrete symmetry that is transforming the different states in the tower, like relating all these states among each other, which is also like a gauge redundancy that is associated to the dualities. And this discrete symmetry also becomes global when you go to the infinite distance. So there are several symmetries that we always observe that appear, that emerge at infinite distance. And I believe that that should always be the case, that in the end, all these infinite distance limits are associated in a way or another to some restoration of some global symmetry. And that's why that's not good in quantum gravity. And that's why the EFT has to break down. But we need to, I mean, something for the future is like to give some fundamental reasoning, some fundamental explanation of why that's the case.
Thanks.
Any more questions?
Can I ask a question?
Yeah.
So, in principle, I could try to prove these conjectures by realizing them in ADS, no?
Mm-hmm. Yep.
So, how much people has been able to prove?
Yeah.
By just mapping it to properties that consistent conformal theories have to satisfy.
Yeah. So for the case of the weak gravity conjecture, this is proven in the case of ADS3 CFT2, because then you can use modular bootstrap, and you can show that the weak gravity conjecture is correlated with the modular invariance of the CFT. This only works in 2 dimensions, because then in higher dimensions, there is no clear analog of this modular invariance. So it's an open question, how to do it in higher dimensions. But at least in 2 dimensions, it's just based on this modular invariance of the CFT. For the distance conjecture, like thinking more of the not on the gauge couplings, but on the large field ranges, we translated this to some statement in the conformal field theory. So this translates to the statement that you should get an infinite tower of operators that saturate the unitarity bound as you move to some infinite distance limit in the conformal manifold measured by the Samolov-Hikov metric. And then you can ask, okay, can I prove that? No, because it's just about following the spectrum of operators. And the point is that all the known examples in superconformal field theories are always also weak coupling limits, in the sense that there is always some gauge coupling that becomes small. And then by Maldacena-Sivoedov, you can show that since it's a free point, because it's the gauge coupling is going to 0, you are going to get a higher spin symmetry. And then this higher spin symmetry, indeed, you get an infinite tower of higher spin operators that saturate the unitarity bound. And since it's a perturbative limit, you can compute explicitly how they behave. And indeed, the anomalous dimension goes exponentially with the distance. So it's proven in that case. So what is missing there is just to show that the only type of infinite distance limit that you can have is these free points. If you can show that, then it's proven the conjecture. If there is any other type of point, which is not a free point, then you need to find a new argument of why you get this infinite tower of operators. And so far, there are no examples. I mean, it would be very interesting to find such example. Personally, I think that maybe there is no example of that type, and it's always a free point. So that would be everything. Okay. Here I'm talking in dimension bigger than 3, in any dimension.
Okay.
Okay, any more questions? Comments? Okay, if there are no more questions, then I think we can thank Irene again. Thank you again for this very nice talk.
Yeah, thank you. Thank you, everyone. Nice to see you again. If you have any question or comment, I'm here. So you can just come and we can discuss physics or whatever.